For problem number 1 in the energy section, we've got a block being pulled by a force on a surface with friction. So we've got a 10 kilogram block. The force being pulled is 100 newtons, a 37-degree angle. It does have a rough surface. Mu is equal to 0.5 and the distance it travels is 5.6. So I like to kind of draw out that visual. Here in part A, I'm going to draw a force body diagram. So I'm going to start with the applied force of 100, then the gravitational force mg, the normal force N, and then the frictional force opposing motion, kind of a cursive F. So that's going to be my force body diagram. I'm going to add components to this as I solve the following parts, but when you draw a force body diagram or are asked to draw a force body diagram as part of your answer, you never want to include components. So this is all they want to see for a force body diagram. How much work is done by the force? So I'm on to part B. Work is equal to force dot distance. The distance being traveled is to the right in the x direction, and so we need to focus on forces that are going or are parallel to that displacement traveled. That's what the dot product here means. It means that the force and the displacement have to be parallel. So I have to break down this force into components. I need the x component specifically for this problem. And so when I break down the components, I usually just write the trig function, but I know that it's going to be 100 times the trig function, which in this case is cosine because it's adjacent over hypotenuse. And then the y component is sine because it's opposite over hypotenuse. So here I am going to plug in the fact that I need the x component, and my equation is going to be a force of 100 cosine of 37 dot the distance, which is 5.6 meters. Cosine of 37 is in your equation sheet. It's 4/5. So we can simplify that down into nice numbers. If I multiply everything out, I get 80 times 5.6, which is 448. And work is in units of joules. For part C, I need to know how much work is done by the normal force. Well, when we look at the normal force dot distance, the normal force is pointing upward. The displacement is pointing to the right. I need a parallel force or parallel component of force, which there is none, and that means that the work here is 0 joules. Same goes for the work done by gravity. There's no parallel component. They're perfectly perpendicular, so again 0 joules of work being done for the force of gravity. But when we go to part E, how much work is done by the frictional force, even though friction is pointing to the left, it's still parallel to the displacement, which is going to the right, so we're going to get a negative work done here. So the force of friction, kind of a lowercase f dot d, is going to actually give me a value, and it's going to be a negative value because friction again is pointing in the negative direction, which by convention is to the left. What we have to do before we solve this problem is figure out what the frictional value is. So friction in your equation sheet is mu n, and mu is given to us, but the normal force is not. So we know that this block is not moving up or down on the surface, and so we know the net force in the y direction is 0. I'm going to start calculating the normal force first, kind of do some side work up here. Normal force is pointing upward. The y component of the applied force is pointing upward, so I'll call that a positive 100 sine of theta. Again, I'm focused on the y component of the applied force, and then I subtract the force of gravity because that's pointing downward. So the normal force is equal to mg. Actually, I'm going to solve that now. M is 10, gravity, I'm going to round it to 10, so that's 100, minus 100 sine of 37, and sine of 37 is 3/5. So when I simplify it down, I get 100 minus 60, and the normal force is equal to 40 newtons. And then I'm going to plug that in here. So let's work our way down. 0.5 times 40 times the distance, and the answer you get for that is, again, I forgot to put the negative because friction's pointing to the left. I get a negative work of 112 joules. Part F is what is the net work done on the block? Well, I have 448 joules of work pointing to the right. I have negative 112 joules of work pointing to the left from friction. I subtract those two and I get 336 joules of work, of net work being done on the block. And then part G is what is the change in kinetic energy? Well, work is equal to change in kinetic energy. And that, I believe, is in your equation sheet. So whatever you got for F is going to be your answer for G. And that's it.